This is Math 30-1, and we are in Chapter 4, where we look at combining functions. In our first lesson, we looked at the graphs of two functions, and we looked at what results we would get graphically if we added, subtracted, multiplied, or divided those two functions. And we considered what happened to the domain in particular, and the range a little bit. And then in 4.2, we looked at algebraically, adding, subtracting, multiplying, dividing the two functions, and again looking at domains and ranges. Ranges we could always get by looking at the graph, but we needed to be careful in case there was a point of discontinuity. We may not necessarily see it on the graph. We would need to know how to figure that out algebraically. In this lesson, 4.3, we are shifting gears a little bit. So we're going to move away from adding, subtracting, multiplying, dividing, those operations on functions, and we're going to look at what are called composition of functions. What that means will become clear as we continue on. So let's just begin with this warm-up question. So we have 4 warm-up questions. I'll have you pause the video and work through these 4 questions given this f of x function. You can pause the video now. Restart when you're done. Well, hopefully you finished. Fairly straightforward. For number 1, we're just replacing all the x's with 2's. And when we replace all the x's with 2's and then simplify our expression, we get 2/5. Number 2. Similar idea, we're going to take our function, and just like I did with the first one, I'm rewriting my function, but everywhere I used to have an x value, in the numerator and then in the denominator squared, I'm replacing it just with brackets. Because a variable is like a brown paper bag where there could be something mysterious inside, or we could change what's inside. In question 1, it was a 2 inside. In question 2, it's a 2x inside. So we replace all the x's with 2x, and then we evaluate or simplify our expression. That's number 2. Number 3, similar idea. I have my f of x function. I'm replacing all of my x's. Again, it's the same function up here, the x over x squared plus 1. Replacing all the x's with brackets. And this time I'm plugging in an x minus 2 in place of what used to be an x. And again, as before, we'll simplify the expression. Question number 4. Basically the same idea, but we're given the information in a slightly different way. Here we're asked what is f of g of x, but then we're told g of x is the square root of 2x. Well, I can replace every x with a g of x. So I have g of x over g of x squared plus 1. But I know each of the g of x's is actually a root 2x. So then I would substitute it in, and I would simplify. What we did in all of these questions, really, but it's a little bit more obvious in 2, 3, and 4, is we did a composition of functions. So here, when I do f of g of x, that is the composition of the functions f of x and g of x. And you'll notice here that there's this different notation used here. So again, just like when we were adding, subtracting, multiplying, dividing, there was a special notation. This f with a little circle and then a g in brackets, all of x, it means f of g of x. There's no mathematical operation in between. It's just defined to be the same thing. Now, if you're someone who has made use of little circles to show multiplication in the past, it's time to change. Because a circle will mean composition of these two functions, a dot would mean multiplication. So we'll need to be careful with that. The domain of this f of x function must include the range of the g of x function. Well, think about what's happening here. As input, my function takes an x value. The g of x function performs some operation on it and it gives output. That output becomes the input of f of x. We'll look at that a little more visually in a minute. The domain of the composition must consider both the restrictions implied by the composition and the restrictions on that inside function. So I can't stick in to g of x anything outside of g of x's domain. That's this second statement. And g of x can't have output that doesn't fit in the domain of f of x. So I have to consider both of these things. Now this idea is going to be a big part of tomorrow's lesson, but I want to start introducing it today just so your brain can start rolling around the ideas. It may not make perfect sense today. It may not be very clear at all, but this is just the introduction to get us started thinking about these things as we'll be looking ahead to tomorrow. When evaluating the composition of functions, it's generally easiest to work from the inside out. Not always, but most of the time. And if you're wondering, just make this a habit and it'll always work for you. Now let's go back to that domain range idea. And we've looked at function machines in some earlier lessons. So we're going to do something similar now. Suppose I have some machine, and this is going to be a function machine. It's going to take some input and it's going to give some output. And let's just imagine I'm going to call this g of x, so that's my function. And let's say my function is a crusher. Let's think about domain and range. Well, here, let me grab a pot. My pot is going to collect my output. So if I'm thinking domain and I'm thinking range, then stuff that goes in here needs to be part of my domain. And stuff that comes out here needs to be part of my range. So let's look at some of the items we have that we could consider here. Suppose I was to take this orange. Could I put this into my crusher and get something out? Oh, yes, I could. I could put in orange and it would crush it up and I would get orange mush out. So I'm going to say this is in the domain. So I'm going to build a little set of items over here that will say, this I'll stick with red. Anything I put over here is in my domain. Let's look at another possibility. Could I take some tomatoes, put them in a crusher, get something out? Once again, I get tomato mush, crushed tomatoes, maybe tomato paste with some pulp and stuff in there. So that's going to work. Well, let's try this apple. Is that apple going to work in my crusher? Yep, I'll get crushed apple out, apple sauce, which is kind of like crushed apple. So all that is in my domain. Could I put a frog in my crusher? Well, no, that would just be rude. Frogs can't go in crushers. They do not belong there. So this is not in the domain. So I'll just make a note up here. This is, get a pen that works, not in domain. Okay, so there's my setup there, not in the domain. This stuff down here is in the domain. Well, let's think about these bricks. Can I put bricks into a crusher? Well, if this is a powerful enough crusher, we could imagine that we could put bricks in here, it would get crushed into little pieces, and we'd get gravel or sand or dust out. So I'm going to argue that, yeah, I'm going to say that my crusher is strong enough to include bricks in its domain. That is pretty powerful. Now suppose I didn't want to stop here. Suppose I wanted to go a little bit further with this whole process. I'm going to move this pot out of the way, and I'm going to not erase that, but I'm going to say, well, what if I want to take that output and do something with it? So that output is going to become input for another function. My other function, I'm going to say is f of x, and I'll say this is a strainer. So as I consider these things that are in the domain of g of x, which of them is going to give me useful output, range values, that can become input for my f of x function? Well, let me just shift this up a little bit. So that's going to be my output, my range from the f of x function, and that becomes part of my domain for the g of x function. So in other words, if I'm going to put these two machines together, the output I get here has to be acceptable input into my next function. So if we think what's going to happen here, I could take these tomatoes, put them in there, crush, 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 get tomato paste out. Tomato paste, can it go into a strainer here? Sure, and it could get strained out, and then the result would be that I could get some tomato juice out. Let's see, can we get that down here? And there we go. So I'm going to say this is acceptable input in this composition of two functions. So let me scroll down a little bit here, and we'll say, well, what is acceptable domain stuff here for this composition of functions? So in black, we'll say this will be the composition of f of g of x. So what's in that domain? And what we've discovered so far is, yep, I can take tomatoes. They will be acceptable input into this system of machines. Suppose I take the orange. Well, maybe I'll scroll up to the top and I'll grab an orange from up there so I can leave that one there. Take this orange, put it in, crush, 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 get orange mush out, stick it in here into my strainer, strain, 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 strain. I get orange juice out. Spectacular. I love orange juice. That is in the domain of my composition of functions. What about my apple? Stick it in, crush, 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 crush. Applesauce out, put it in the strainer, strain, 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 and I get apple juice out. Yep, that will work in the domain here. Now suppose I take the bricks and I stick the bricks in here, crush, 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 and here I get output of gravel. And I put gravel in my strainer and it just gungs the whole thing up. I don't get anything useful out of here. Unless I'm looking for dust, well, that's potential. But I'm going to imagine that this combination of two machines is actually a juicer. If it was a juicer, then I'd say, this does not fit in the domain for my composition of functions. It's not giving me anything useful. So that's going to be left out here. So notice that when I put my two functions together, and let's see if I can draw a composition of these functions. We'll go with purple, and I'm going to make it fatter. So I'm going to build all of this into a single machine. So here's my machine. There we go. There it has its big input thingy. And here's the big spout at the bottom. So this whole purple thing is a single machine now. And that single machine is this f of g of x composition of functions. Now, what I needed to do is I thought about what can go in here is I needed to think about what can g of x take. It couldn't take frogs. So frogs were rejected. But then I also had to look at this point and say, oh, what can this f of x function take? And in my argument, I said it couldn't take the brick dust and crumble and stuff. So I had to consider those 2 points in order to figure out the domain for this composition of functions. So hopefully that gives you a clearer idea. We'll see more what that looks like in examples tomorrow. This gives you something to ruminate on before then. Let's go back to composition of functions in a variety of different forms. So in this form, we're looking at mappings. So here we're saying if I have inputs of x, then g of x will give me these outputs. If I have these inputs of x, then f of x will give me these outputs. So given that, here I'm asked to find what is f of g of -1. Well, as I mentioned on the previous page, what we want to do is we want to start from the inside and work out from there. So I have this innermost value where x is equal to -1. That's going to go into the g of x function. So I'm taking this -1, that's my input. What do I get as output? I get this 2 as output. This 2 is now going to become input over there. So here I'm going to put a 2 because g of -1 equals 2. And now I want to find what's f of 2. Well, I took that input of 2 here that was the output from the g of x function. I plug it in and I get 3 as my output. So the result of that composition is that I get 3 as output when I put -1 in as input. And that's how a mapping notation would function in this composition. Notice that when I started this question, it was given in this notation, f with a circle g, and then of -1. Notice this isn't -1 times that. This is function notation. This is f of g of -1, and I rewrote it this way just because it's easier for my brain. This is more familiar to us at this point. Always a good first step. Let's look at another example where we're given tables, basically the same thing. So here I can see that I have this mapping. Notice this time I don't have the brackets, but again, just like before, this is saying that I want to find what is f of g of 2. So let me pause here, let you pause, and take a few minutes, try these 3 questions, see what you get as final output, and then restart the video. Here we go. So here I've written the f of g of 2 again, and I color-coded it to make life a little bit simpler for me. Again, I look at the input. Here I start with the 2 as my input into the g of x function. So make sure we're looking at g of x. I input 2, and I get a -2 out. That -2 becomes my next input. So this is a -2. That becomes the input into the f of x function. So this -2 got plugged in, and what I get out is a 12. Let's look at number 7. So here for number 7, I'll drag that over there. Whoops, this is the last one. That's not this one. Getting ahead of myself here. So here I've color-coded it. I'm going to plug this -4 into my f of x function. That gives me a 3 as output. So my next line, green, will be g of 3. And then we evaluate that. See that when I plug 3 in, I'll get a -5 as my output. And then number 8, we can do a composition of a function with itself as well. So f of 4, I can rewrite it like this. What is f of 4? F of 4 equals 0. So I plug in the 0 and find out, oh, what's f of 0? That's equal to 2. There's my answer. On to the next page. Just like we did with adding, subtracting, multiplying, dividing, we can work from graphs as well to do the composition of functions. So that's what we'll do here for questions 8 and 9. Question number 8. The input that I'm sticking in is a -2. So that's an x value. And so what I'm going to do is I'm going to say, well, when x is -2, I'll use a vertical line to help me. I want to know what is the value of the g of x function. Got to line up a little better. Okay, and there we go. So I have that input. My input is a -2. I come up here. What does it give me as output? It gives me 8 is my output. So this is saying I want to find what is f of 8 because this inside part, the g of -2, that was equal to 8. So now this y value becomes an x value. And the x value is an 8, so I'm going to move this over here, and we'll say, oh, pardon me for a moment. Now, where was I? So we just got this g of -2 equaling 8, plug it into the f of x function. That becomes my new x value, and I want to see what is the output I get. The output is a y value, and that y value is here. Looks like a 3 as I come across, and I look to see what the output is. So this is equal to 3. Why don't you pause the video and you try question number 9. Restart when you're done. Well, I started by rewriting it just because this notation is a little bit simpler for my brain. So I start with this input of 3. So I look here and see what input of 3, and my f of x function is operating on this, so I'm looking at the red function, and I see that when I plug in a 3 as input, output, I get a 2. So this is equal to g of 2. That 2 now becomes input. So input into the g of x function, which gives me output of 0. There's the composition of functions graphically. Now let's look a little more algebraically. Question number 10. I want to find g of f of 3, where I'm given this function f of x, 4 over x minus 2, and g of x, 2x squared. Well, I'm going to start here with finding what is f of 3 equal to. So I take this and I replace all the x's, there's only one x, with a 3. And so that gives me 4 over 3 minus 2, which is 4 over 1. Looks like it's just a 4. Well, there's my output from the f of x function. Now that's going to become input into my g of x function. So that 4 becomes input here, which means I'm going to take that 4, square it, and then multiply by 2. 4 squared is 16 times 2, 32. There's the result that I get from the composition of g of f of 3. On to number 11. Here again, I'm rewriting it as f of g of x because that is easier for my head to handle. And then I'm going to look and see, well, g of x is 2x squared. So this is just like the warm-up questions. In this question, I had a number to plug in, and I could evaluate it and then plug that in to my g of x function, evaluate that. Here, I still have the x's. So I just plug those in and see where this takes me. So now my input is going to be a 2x squared. And can I simplify this? Well, I think I can. If there's a common factor of 2 in the denominator, so this is equal to 4 over 2 times x squared minus 1. The x squared minus 1 can factor as well, but I can see that there's not going to be a common factor in the numerator other than just the 2 that I canceled out there. So I end up with 2 over x squared minus 1 being my composite function. So what I've done here is essentially I've built a machine out of these two smaller machines. It's kind of like I had this being my crusher and this being my strainer, but I built them together into my juicer. So this is the composition of functions. So we could use that notation that f of g of x is equal to 2 over x squared minus 1. So this is how we could write our final answer using that composite function notation. At this point, why don't you pause the video and do these next two questions. Restart it when you're ready, and that'll be the end of the lesson. Well, here we go. I'm going to start with this inside function. What is g of 9 equal to? Well, I look and see, oh, here's my g of x function. And so I'll replace this x with a 9. So I'll have 9 minus 3, which is 6. That will be squared, which will give me 36. That output becomes input into my f of x function. My f of x function takes the square root of that x and adds 3 to it. So I'm doing the square root of 36 and then adding 3. Square root of 36 is 6, and when I add 3, that gives me 9. So interesting that my input is the same as my output. In other words, whatever the g of x function did, the f of x function undid. When we have two functions, one undoes what the other one did, what do we say about those two functions? That's for you to recall. I'm going to go on to number 13. Here we go. So I have the g of x function as the outside function this time. And this time there aren't brackets there, so my inside function is this green one. So I switched colors here. The square root of x plus 3, that goes inside this bigger function. So unlike the previous question, I didn't do this in-between step where I wrote f of 2x squared. Here I didn't write g of whatever the f of x function was. I just did it all at once. And with practice, we can save some steps. And again, we see here that I can get rid of those brackets. The 3's cancel out. I square something square rooted, and I get x as my output. So again, I can see the composition in this order. The g of x function undid what the f of x function initially did. There we go. That would be the end of this lesson. And we have a few questions down here for you to practice in your workbook. Enjoy!